Good afternoon, everyone. Today we will go to our next session, Introduction of the Chemical Kinetics Part 2. The course code is BCHCT137 and the course name is Coordination Chemistry, State of Matter and the Chemical Kinetics. So let us start. Myself Vishal Singh, School of Sciences, IGNOU. In the previous lecture, we have covered the topic Introduction, Chemical Kinetics and its significance. What is the chemical kinetics and what is its significance? How we call it as a chemical kinetics, and role of the chemical kinetics, defining rate of the reaction. What is the rate of the reaction? How to calculate the rate of the reaction? How to measure it? And which factor affect the rate of the reaction? These parts we have covered on our previous lecture, and today we will start differential rate law, which is the part of our rate laws, order and the molecularity of the reaction. What is the order? What is the molecularity of the reaction? Because these two are not the same. And integrated rate law, which follows zero order reaction, first order reaction and the second order reaction. Now this, after studying or after listening this, you should be able to explain the differential integrated rate law and outline their significance. You can also define the rate constant and the chemical reaction, differentiate between order and the molecularity of the reaction. You can also define the order of the reaction and outline its significance and its unit. And you can also analyze the integrated rate equation for zeroth, first and the second order reaction. And you should also learn here what is the half-life and in respective what is the half-life for zero, first and the second order reactions. Then in the previous lecture we have taught, we are consider what are the rate law. So here we again some gist we have given. So rate law is the relation between the rate and the concentration or the initial concentration, or whatever we can say, the concentration of the reactant of the reaction. So it is basically the relation between the instantaneous reaction rate and the concentration of the reactant. Here we have given the two example, where the rate is equal to some units, which is we have given K. Later we can introduce what is K, and this symbol is designated at the concentration of the nitrogen pentaoxide. It is the power 1, means rate is directly proportional to the concentration of the nitrogen pentaoxide. And in the second example we have given the rate is equal to K into concentration of Hi to the power 2, means here the rate is directly proportional to the second power of the initial of the instantaneous concentration, or the concentration of Hi to the power 2. So here these two equation we had basically denoted at the rate law. It's basically give the relation between rate and the concentration of the reactant. In general, if we can say that rate is equal to some constant into concentration of reactant to the power some power, which power we can designate it at the order of the reaction. Here for a simple reaction, whatever we have given, for A give the product or something, reactant give the product, the where basically this order is denoted by the P, what is the power of the concentration to the power. And here K is introduced at the rate constant or the coefficient. Sometimes it is called the rate coefficient or the specific rate constant. Here we can say the specific rate constant. If the concentration of reactant is unity, then the rate is directly equal to the K, which is the rate constant. So for the unit concentration, the reaction rate is directly equal to the K. Therefore, the K is also termed the specific rate constant. Here also say that K is the proportionality constant. Here K we are saying it is constant, but it is independent of the concentration, but it may depend on the temperature or the catalysis of the reaction, or whatever the pressure is there. We will learn this effect of pressure and temperature later, but this K is termed as the specific rate constant or the rate constant, which is independent of the concentration. Let us consider some other example, like some reactant A plus B plus C give the product. The rate is directly equal to K, rate constant, and concentration of A to the power some power P plus concentration of B to the power Q plus concentration of C to the power R. Then we can consider the overall rate of the reaction is whatever the power of the reactant. It here the concentration of A to the power P, B to the power Q and C to the power R. Then the overall reaction order we can write it as P plus Q plus R. Basically it is the sum of the powers of the reactant concentration. But it in the previous lecture we have showed that it is not directly calculated from the reaction. It is calculated from the experiment. So let us take an example. 2 mole of nitrous oxide plus Cl2, which is gas, gives the 2 NaCl. Here the rate is equal to rate constant into concentration of reactants, which is in respect to the NO to the power 2 and Cl to the power n. The overall the rate of the reaction we can term as 2 plus 1, which is equal to C. So this reaction have the order of 3. Now what is the unit of this rate constant in the rate law? So for the we have listed here for the 0 order reaction and what for the first order reaction, for the second, third and as well as for the n order reaction. The rate law is the simplest rate law we have given for the 0, first and higher orders for this one. So for the 0 order reaction, the unit is given at here the A to the power 0. Whatever the reactant concentration is A to the power 0 for the 0 order reaction, it is 1 and the rate is directly equal to the rate constant. So whatever the unit of the rate is equal to the rate constant. So here the unit is for the rate constant is given at the mole decimeter to the power minus 3 and the second inverse. Similarly for the for the first order reaction, it is simply the second inverse, and for the second order equation, it will give the mole inverse decimeter to the power cube into second inverse. If we derive it for the nth order term, then we can simply say that the unit of the rate constant is basically mole to the power n minus 1 decimeter cube to the power n minus 1 and the second inverse, where n denotes the order of the reaction. Similarly for this the below reaction, whatever we have given for the 3/2th order reaction, we can calculate the unit of the reaction, because here we have taken the n is equal to 3/2. Simply we put this n is equal to 3/2 in the nth order reaction and we can calculate the what is the unit of the rate constant. So here for 3/2th order reaction, the unit is mole to the power minus 1/2 decimeter to the power cube to the power 1/2 and second inverse. So basically in the differential rate law we have covered, and here the most important part we are going to cover is order where the molecularity of the reaction. What is the order of the reaction and what is the molecularity of the reaction? So in the previous lecture also and today also we say that the order of the reaction is determined from the experimental rate law. Simply by seeing the equation we can't define what is the order of the reaction. We must perform the experiment and we produce some data. On that basis we can say that this is the order of that reaction, whereas molecularity is the number of molecules involved in step leading to the chemical reaction. Whatever the number of molecules involved in this reaction, basically the reactant molecule, this is the molecularity of the reaction. We have given some example here. See the first example where 2HI gives H2 plus I2. The rate law we have given rate constant into HI to the power square. Here the experimentally found the order of the reaction is 2, and here we can simply by looking the chemical reaction we can say the molecularity is also 2. But for all the cases the order and the molecularity of the reaction is not, it should be different. Let's take the another example. 2NO plus Cl2 gives 2NoCl. Here the order of the chemical reaction is 3 as well as the molecularity is also 3. But if we move to the next example, then we can say that for the chemical reaction where the decomposition of the nitrogen pentoxide occur, here the rate law is K into concentration of nitrogen pentoxide to the power 1. Here the order of the reaction is 1, but the molecularity is 2 because 2 mole of nitrogen pentoxide is used. Similarly for the fifth example, if we can say that the order we have given it is 4, which is from the experiment, but from the molecularity we can see that 1 mole of BrO3 minus is used, plus 5 mole of Br minus and plus 6 of S plus is used. If we add the moles of the reactant, then we found that 1 plus 5 plus 6 is equal to 12. This means here the order of the reaction is 4, but the molecularity is 12. Similarly, some example also we have given. Here the order hydrolysis of ethyl acetate and hydrolysis of sucrose, here the order of the reaction is 1. But if we calculate the molecularity of this reaction, so similarly by seeing the reactions we can calculate what is the molecularity. For that case it is 2, because 1 mole of ethyl acetate and water is used. Now we move to the what is the integrated rate law. In the differential rate law, whatever just we have covered, here we can see the relation between the rate and the concentration. Whatever the at the concentration increases, the rate should increase. But in integrated rate law, if we want to calculate the concentration of the product, if the reaction is going on, then we can calculate the concentration at any time t. If we know the nature of the reaction, we can directly calculate from the integrated rate law we can calculate the concentration of the product at any time t. So we start from the zero order reaction. In zero order reaction, some example we have given: the decomposition of ammonia on the hard platinum surface and the decomposition of nitrous oxide on the hard platinum surface. This is the example of the zeroth order reaction. For the simple reaction, let's say A gives the product, then the differential rate equation is defined through this reaction. The concentration of the reactant at a given time t is equal to rate constant into concentration of the reactant to the power 0, because it is zero order reaction. And here we put the negative sign because we write the rate equation in terms of the reactant. If we solve this equation simply by using the integration method, we can solve this equation differential law, and it gives A to the power t, means concentration at a time, concentration of A or the reactant at time t gives minus k into t, k is the rate constant, or plus initial concentration of the reactant. If we plot the integrated rate law for the zero order reaction, concentration of A at time t versus the time, then the intercept is simply the initial concentration of reactant, and the slope is equal to minus k. So from the graph we can also calculate the slope of the reaction. For the plotting, simply we can calculate the linear line plot, means y is equal to mx plot. So m, whatever the slope is there, it is minus k, and whatever the intercept is there, it is initial concentration of the reactant. Now we move to the half-life. What is the half-life? Everyone know what is the half-life. The time taken for the concentration of a reaction to fall to half its initial value is called the half-life of the reaction. It is denoted by the symbol T in the subscripts 1/2. Again, for the same reaction, whatever we have discussed earlier, A gives the product, and the rate equation we have given at time t is equal to t half, means exactly what the time, when the time will become half, then the concentration of A is defined by initial concentration of A0 by 2. So by putting the simple these two at in the above rate equation, then we find T is equal to initial concentration of the reactant divided by 2k. Here we can say that the T half is directly proportional to the initial concentration of the reactant. From the plot also we can see that if we plot the concentration of A versus T plot for the zero order reaction, then we can say it is the decreasing trend, means it is decreasing half-life, means initial the half-life is higher, after the second half-life it is lower than the first, subsequently the third one is lower from the second. So means we find the decreasing half-life trend. And next we move to the first order reaction. Here the some example of the first order reaction: decomposition of the nitrogen pentoxide. This example we have seen earlier also. Decomposition of the hydrogen peroxide also. And similarly, if we derive the rate equation for this first order reaction from simply assuming the considering a reaction A gives the product, then the differential rate equation is just K into concentration of A to the power 1, because it is the first order reaction. And simply integrate this equation, we found that A at time t, concentration of A at time t is equal to initial concentration of A, means whatever the reactant is there, e to the power minus kt. If we simplify this term, we will get K is equal to 2.303 by T log of initial concentration of A divided by concentration of A at time t. Here 2.303 is found from the ln. If we convert the ln, means e to the power log, so then we find the 2.303. Again, if we plot using y is equal to mx plus c linear line plot, then these plots are showing plot of the integrated rate law for the first order reaction. Then again we found the slope is equal to minus k. For if we plot log a naught by t at versus the time, then the versus t, then the slope will be k. So rearranging this term and the plotting a versus t, we found the rate constant of the reaction for the first order reaction. Again we can calculate the half-life for the first order reaction. Similarly, whatever we have the rate equation is there, simply by putting the concentration of A is equal to A naught by 2, means initial concentration by 2, and putting the value in the rate equation, we will calculate the T half is equal to 0.693 upon K. You must have solved some radioactive problem, which is the first order problem. You can calculate the half-life for the radioactive decay. This is the important example for the first order reaction. Here you can directly see that T half, the half-life, is independent of the initial concentration of the reactant. Means here you can say that whatever the half-life for the reaction which is falling in the first order reaction, it is independent of the initial concentration of the reactant. Here from the graph you can also see that if we plot a curve, concentration of A versus T plot for the first order reaction, here you can show that the constant half-life, means for the first half-life is exactly similar to the second half-life, which is similar to the third, and so on so forth. So means here the half-life for the decaying, it show the consistency in the first order reaction. Now we move to the pseudo first order reaction. What is pseudo first order reaction? A pseudo first order reaction can be defined as a second order or the biomolecular reaction that is made to behave like first order reaction. This reaction occur when the one reacting material presence is great excess in its and maintain at a constant concentration compared with the other substances. Simply, if you consider the reaction A plus B which gives the product, if the component B is in large excess in this reaction and the concentration of B is in very high as compared to that of the A, the reaction is considered to be pseudo first order reaction with respect to A, or the vice versa. Means if the component A is in large excess and the concentration of A is very high as compared to B, then this reaction is considered to be the pseudo first order with respect to the B. Simply this is the best example of the pseudo first order reaction where the hydrolysis of ethyl acetate. So here we can say that at time t is equal to 0, the concentration of ethyl acetate is 0.02 mole per liter if we start from there only, and the concentration of water is 20 mole per liter, and the initial concentration of the product is 0. After time t, all the concentration of ethyl acetate is converted to the product, that's why it becomes 0, and the concentration of H2O it decreased from 20 mole per liter to 19.8 mole per liter, which is very less amount. Means after completion the reaction, very little amount of solvent is used, or the whatever the in the initial we can say that the second reactant is used, the excess amount of water is used, then this reaction is pseudo first order reaction, means it is look like a second order reaction, apparent second order reaction, but actually it is the first order reaction, this pseudo first order reaction. Here the rate is defined by K, rate constant, into the concentration of ethyl acetate and the water. Since water concentration doesn't vary because it is in excess, so we introduce K into H2O is equal to K prime, means some other rate constant, and the rate, then the rate is directly rate is equal to K prime into the concentration of ethyl acetate only, means the rate is directly proportional to the ethyl acetate only, not the water, because it is in the excess amount of water. If we move to the second order reaction, similarly this is the formation of hydrogen iodide, nucleophilic substitution reaction, and for the reaction, if we consider it is A gives the product is a second order reaction, then the differential rate equation, after solving the differential rate equation, the equation is given as 1 upon concentration of A at time t is equal to Kt plus concentration of A0 to the power inverse, and the half-life for the second order reaction T half is denoted by 1 by K into A naught, which is here we can say that the half-life for the second order reaction is inversely proportional to the initial concentration of the reactant. So here from the trend of the concentration of A versus time, it shows that the for the half-life for the second order reaction showing the increasing half-life. Here as the time increases, the half-life increases, means the first half-life is lesser as compared to the second half-life, and which is also the second half-life is also lesser from the third half-life, and so on and so forth, means we get the increasing trend. So if we compare the zero order reaction, first order reaction, and the second order reaction, the half-life is gives the some changes. Like in the first order reaction, it show the constant all over the time. In the second order reaction, it is give the increasing trend, and for the zero order reaction, it gives the decreasing trend. From the half life of the reaction, we can also calculate and indicate and determine what is the order of the reaction. And if the summary for the zero order reaction, first order reaction, and the second order reaction, differential rate law is given. For the zero order reaction, it is directly proportional to the rate constant, and for the first order reaction, the reactant are A to the power 1, and for the second order reaction, it is A to the power 2. And here we have given the integrated rate law for the zero order reaction, first order reaction, and the second order reaction that we have discussed. And T half also we have given, because the in T half for the zero order reaction, the T half is directly proportional to the initial concentration of the reactant, and it is independent for the first order reaction, and it is inversely proportional to the second order reaction. And the type of plot we also discussed, and the unit whatever we have given for the zero, first, even for the nth order reaction and the fraction order reaction, we have given the unit of the rate law or the rate constant. So here we have discussed the differential and integrated rate law. In integrated rate law, we have discussed the first order reaction, second order reaction, and the third order first, zeroth, and second order reaction. In the next discussion, we will discuss what the temperature effect of the rate constant, and how we determine or the method to determine what is the rate constant of the reaction, or method to determine the order of the reaction. Some methods are there where from the experimentally we can calculate the order of the reaction, and some theory like activated complex theory, Arrhenius theory, and the collision theory, we will discuss it in the next session. Thank you. If you want to email or ask some question, you can write to me at vishalsingh@ignou.ac.in. Thank you.